putting in the morphine or in the benzomorphines to give us antagonistic activity. The other group, which is still part, it still has similarity with the 4-phenylpiperidines, is what we are calling the anilidopiperidines. I had mentioned it. And in the anilidopiperidines is just where you insert a nitrogen. So between the piperidine ring, this is our piperidine ring here, and the phenyl ring, you insert a nitrogen. And once you insert a nitrogen, as I had said earlier, the phenyl ring is supposed to take the axial orientation. But because of energy constraints, the concentration of the axial conformer is very low. When you put the nitrogen, somehow it allows the phenyl ring to be able to attain, it allows the molecule or the phenyl ring to be able to attain the axial orientation. And because it's the axial orientation, then you find those molecules or those resultant compounds have much, much higher activity. So the nitrogen allows this molecule to get the optimal conformer or the optimal structure or the structure that is best required, or that is the structure which is best for optimally binding the receptor. So just insertion of that nitrogen where it is between the piperidine ring and the phenyl ring allows that molecule to attain the structure which best or optimally binds the receptor. And that's how you get fentanyl. You can see, as we had said, fentanyl at this position, at position number one, at position number 1, it has a hydrogen, and then it has that group. When you look at these others, at that position, it has this group and it has another substituent, and that is the main difference. So moving the phenyl ring from direct attachment, the pyridine ring by one atom of nitrogen on the side chain allows for the phenyl ring to assume the more favorable axial conformation. Thus, the phenyl ring of the anilidopiperidine binds a D site similar to morphine, to the morphine A ring. So it is able to bind. So the D ring, the phenyl ring of the anilidopiperidines is able to bind equivalently, just like the way the A ring of morphine binds the A ring of morphine binds the D. The A ring of morphine binds the D site. Remember, the D site is where the phenyl ring binds through hydrophobic binding. The 3-hydroxyl group is not essential for binding to this site, this class, and therefore you find these compounds do not have the 3-hydroxyl group because they do not bind they do not bind the hydrophilic site of the morphine receptor site. They don't bind, so they are only using their aromatic ring to bind the D site, and therefore you do not require the 3-hydroxyl group is not necessary. And these drugs are some of the very potent synthetic analgesics. And as I had said, indeed, these are drugs like fentanyl is used as a general anesthetic. Some of the very, very potent analgesics, and you have fentanyl as a general anesthetic. You can see fentanyl. It's very, of course, we cannot remember how many times, but it is more potent than morphine. It has very high mu receptor affinity due to binding of A, B, C, and D. So it binds all the receptors. It's able to bind all the receptors. Remember, morphine does not bind the A receptor very well. Yet it's only when you put big substituents at the terminal nitrogen that it's able to bind the A receptor. If you look at this drug, they already have a big substituent at the terminal nitrogen, so they can interact with the A receptor, they can interact with the B receptor, they can interact with the C and D receptors. It has a high lipid water partition coefficient, and then can be absorbed through skin or oral mucosa. If you look at this compound again, that is highly lipophilic. The groups that are bringing water solubility are small, and therefore the compound having very high lipid water partition coefficient, absorbed through the skin or oral mucosa. The nitrogen at carbon 4, as we said, is able to align the molecule, and the alkyl, it's nitrogen at carbon 4 and the alkyl, The nitrogen at carbon 4, that's the nitrogen at carbon 4, and the alkyl. And the alkyl, I believe this alkyl group, alkyl, nitrogen, carbon 4, and the alkyl through a bond increases. We are only saying just what we have said, they are only putting it differently. We are only saying that this nitrogen is able to give as the best conformer. You're saying it's able to align nitrogen, carbon 4, and the alkyl through NCO, but increases mu receptor affinity by correctly orienting the phenyl ring. So this nitrogen here through the alkyl, through the NCO. This is the NCO. So nitrogen and the alkyl through the NCO. That nitrogen and this alkyl through the NCO is able to give this molecule the best orientation. But the easier way to do it, to say it, is just once we put the nitrogen between the phenyl and the piperidine ring and the other substituents, which the other appropriate substituents, then you find that this molecule is able to attain the conformer that best fits, or that best fits the receptor, or that best fits the receptor by giving us the proper orientation of the phenyl ring. Ramifentanil, esters or nitrogen, and at carbon 4 lead to rapid inactivation by plasma. So if you look at ramifentanil, this is a ketone. This is a ketone, that lamifentanil. So if you look at lamifentanil, you have that is an ester there. That is an ester there. And because when you have an ester, esters are readily hydrolyzed. Esters are readily hydrolyzed. So because of that ester, readily hydrolyzed. And you can look at the other compound, some of the other anidopiperidines. That's why we say, that's why we are changing the group at that position. You can see for, we have the ramifentanil. I have fentanyl, which has a hydrogen. I have lofentanil, which has an ester, which will be readily hydrolyzed. Safentanil, it has a ketone, so it acquires stability. So the change in this group here is to try and acquire, as we have said, change in this group is to try and acquire stability so that the compound is not readily hydrolyzed, to give it a very short duration of activity. You can see this one, that one, and that one. The group there is kind of the same. We are also saying you can't change. You look at fentanyl, it has a phenyl group. Of course, also fentanyl, look at fentanyl, also has a phenyl group. But when you look at this other compound, safentanil, alfentanil, have isosteres. Safentanil and alfentanil has isosteres of the benzene ring with retention of activity. But we do know the one which is readily used as a general anesthetic is actually fentanyl. So there we are saying you can have different substitutions. You can have substitution at the terminal nitrogen. You can have substitution on the nitrogen, both on the aromatic ring, where you can put an isostere, and also on the nitrogen, on the ester, or making it an ester or a ketone. The ketone just gives stability because esters are very readily hydrolyzed. Esters are very, very readily hydrolyzed. I think, if I'm not wrong, that will be the end of the phenyl piperidines, where we have discussed the phenyl piperidines, we have discussed the bemidones, we have discussed the prodines, and also we have mentioned the anilidopiperidines. And now we are saying the anilidopiperidines is where you put a nitrogen between the phenyl group and the piperidine group, allowing that molecule to give us the phenyl ring in the axial position, because the axial position allows for binding of that molecule to all the sites of the morphine receptor. And I think I can remind you, the morphine receptor We had already looked at it before, but we can always, there is our morphine receptor. Remember, we say this is our site this is our site C, again, which is bound still by the lipophilic portions of the molecule. Site C, so it's lipophilic. Site B is the one which is anionic. And of course, we have the site A. And the site A, as we said, is bound, especially when you have a phenyl group at position at the terminal nitrogen. When you have a phenyl group, especially at the terminal nitrogen, that is when you are able to bind your site A. So that is why we are saying when you change the structure of these compounds and you change the way this molecule, one is positioned in terms of the orientation of the phenyl ring. If you attain an axial position, the better, because attaining the axial position naturally from a pyridine, as we said, is a bit difficult because of the energy levels. The axial position has a higher energy level than the horizontal conformer, and therefore the axial conformer exists in very, very low concentrations. And because it exists in very low concentration, its ability to bind the receptor, there will be very little to bind the receptor. Of course, when the little binds the receptor, more, of course, of it usually there will be an equilibrium. More of it is formed. But of course, the little concentration will have a negative influence on its ability to bind the receptor. So with that now, unless if there is any query, we move to the next group. Move to our next group, and then our next group, let me check whether there is any query. Then as I check how many of us have signed in, somebody has just left. Let me save how many of us are there. We are now 31. So not signed in again. So now we move on. I think this might be almost the last group, and the last main group of the morphine derivatives is where now we open up. We have the piperidine ring, but we as in the 4-phenyl piperidines, it's a closed ring. Now we open up the piperidine ring. We still retain the benzene ring. We open up the piperidine ring. So these are straight chain derivatives. So we open up the piperidine ring and we have straight chain derivatives, and they were still found to have activity. They were still found to have activity. Kindly look at their structures, draw the structures of methadone draw it out as a home exercise, and find out and try to see whether methadone still obeys the morphine rule. So draw it out and find out whether it still obeys the morphine rule. So we are looking at the phenyl propyl. You can see propyl means. And remember we did say propyl is, you see we have the propyl. Remember we did say even for the phenyl piperidines, ignoring the oxygen, the propyl group gave us maximum activity. So you can see that is to maintain phenylpropyl means, also called diphenyl heptanones. So this is their general structure. That is their general structure. And of course, of importance, you can see we still have our phenyl ring there. And then you have different substituents. The 4 substituents can be different. But if you look at our R4 in all of them, kindly look at our R4 in all of them, you see that our R4 will have a nitrogen. There is a nitrogen, there is a nitrogen, there is a nitrogen, and even there is a nitrogen. The groups can be different, but all of them still have a terminal tertiary nitrogen. If you look at the R4s, like if you look at the first one here, the difference between methadone and isomethadone is that in methadone, if you look at methadone, you look at this, you count from this nitrogen, it is the alpha carbon that is branched. So it looks like branching is important, and even the position of branching is important. If you look at methadone, it is the alpha carbon that is branched. If you look at isomethadone, again, there is branching, but this time the branching is on the beta carbon. On the beta carbon. If you look at no methadone, If you look at normethadone, in normethadone, there is, so that is there is no substitution. In normethadone, there is no substitution. In other words, there is no branching rather. In both isomethadone and methadone, there is branching. In normethadone, there's no branching. And then, of course, when you look at dipanone, there is a piperidine ring. The tertiary nitrogen, or tertiary nitrogen, is part of a cyclic ring or heterocyclic ring, which is piperidine with retention of activity. We look at R2. So one of importance is to note that our tertiary nitrogen is still there. So although we have opened up the piperidine ring, and of course our tertiary nitrogen is still there. So that tertiary nitrogen is still in agreement with what we required earlier. If you look at methadone, R2, so you have this carbon there, you can have two substituents there. You can see R2, one is an ethyl group and the other one is a ketone and an ethyl group. Again, methadone, this is not, it's not an ethyl group. I don't know what I was saying. It's a benzene ring, sorry. So you have a benzene ring, so it's a diphenyl benzene ring and a ketone. And then you look at isomethadone, again, those are the same. So the only difference is that methadone and isomethadone are constitutional isomer. They are constitutional isomers and more correct constitutional positional isomers, because it's the position of the methyl group that is different. The length of the chain is the same. It is the position of the methyl group which is different. So constitutional positional isomers. Otherwise, everything is the same. Again, the structures here are a bit simple. Again, the same. The only difference is that in this one, it has 1, 2. It is not substituted. When this is isopropyl, this is an ethyl group. That's isopropyl. That is an ethyl group with retention of activity. As we have said again here, look at the structure is the same. So all of them, no wonder we are calling them diphenyl heptanones. Again, the structure is the same. It's only that the nitrogen is part of a piperidine ring with retention of activity. Oh, I didn't remember to make this one big, so let me make it a bit bigger. And then you have alpha acetam methadone. Again, it is that group there. That is a bit different. That group there is what different. Dextromoramide, again, it is that group there, and of course, and the final group is different. You can see the terminal nitrogen is part of a morpholine ring with retention of activity, and phenodoxone, again, the same. Have the morpholine ring, but of importance is that we still do have in all of them a tertiary nitrogen. Then you have propoxyphene or dextropropoxyphene. This one, the dextropropoxyphene, has much lower analgesic activity. The liver one does not have any analgesic activity and is actually used as an antitussive. So you can see the difference here is that our benzene ring has been replaced with our phenyl ring. The benzene ring R2, you can see it's a benzyl ring here, C6H5CH2, a benzyl ring there. This is an ester, OC double bond OC2H5, so that's an ester. And again, this has the same structure as isomethadone. That's the same structure as isomethadone. There's a difference in that. You have one benzene ring, but the other one is a benzyl ring. And then, of course, it is an ester, and of course, to the terminal nitrogen. I think I did draw the structure of that one so that we can be able to appreciate the difference. Oh, I thought I'd do the structure. Yes, here is a propoxyphene. They say it is usually formulated as napselate. This is a napselate. The reason why Again, they formulate. You can see it has very high lipid solubility. The reason why they formulate this way is to avoid it being abused, abused. So they formulate it as a propoxyphene napsylate. So again, if you look at it as we were saying, you can see it has one. This is a benzene ring, phenyl ring. Remember, there were two substituents at this position. One and the other one is a benzyl ring. In all the other derivatives, this was a phenyl ring and that was a phenyl ring. And therefore, this carbon was not a chiral center because that was a phenyl ring and this was a phenyl ring. So that carbon did not have four different substituents. But in propoxyphene, that is a phenyl ring, that's a benzyl ring. All these substituents are different. So that is why we are saying that carbon is a chiral center and can exhibit optical isomerism with the dextro isomer having analgesic activity and with the levo isomer having only antitussive activity. So you can see again how the difference in structure, can bring a lot of differences. And of course, this is what was our piperidine ring, but now it's an open chain. So of course, that group there attached to a CH, you can see branching beta to the nitrogen. That is alpha beta to the nitrogen, and then of course CH2, and then our terminal nitrogen, which indeed is to a tertiary nitrogen, which definitely is readily protonable. I wanted us to see that structure so that we appreciate the difference in structure in propoxyphene compared to the other compounds. So we just look at that. So we are saying the prototype is methadone. It can be viewed as a ring D opened, as we have said. The ring D is what we had in morphine. Morphine was piperidine ring was ring D, and it has been opened. So as ring D opened in our piperidines, when ring D of morphine was opened, there is a total loss of activity. But racemic methadone is equal to morphine in analgesic activity. So we are saying, remember when we were looking at morphine in the SAR, as morphine, all the rings are important for activity. So as morphine, you cannot go and open ring D. It will not have activity. But when you structurally modify morphine through the phenylpiperidines now to the propyl amines, in other words, the phenylpropylamine, the open chain, when now you modify, remove some of the rings, remove ring B, remove ring C, remove also the E ring, and now you can open up the piperidine ring. So once you open up the piperidine ring, you no longer have morphine and analogs. Now you have the propylamine analogs. And of course, the prototype, as we are saying, is methadone. And you can see it has equal activity as morphine in analgesic potency. But phenyl rings are required. Phenyl rings are required for potency. Removal of one sharply reduces potency and may help correct positioning of one phenyl ring, correct spacing. All we are saying is that, again, for maximum analgesic activity, you do require the two phenyl rings. If you remove one, or if you change, like you have changed in propoxyphene, whereby one of the phenyl rings has been replaced by a benzyl ring, then you have changes in activity. Again, because that change will alter the position or will change the shape of the molecule and its ability to interact with the receptor. That's all we're saying. So it will change the spacing, it will change the shape of the molecule. And remember, the terminal nitrogen is protonated at physiological pH. So it will change the spacing, it will change the shape of the molecule, and the terminal nitrogen will not be able to interact with its anionic site. It will not be able to interact with its anionic site, and I think that anionic site is the site C, not be able to interact with its anionic site C, and therefore the molecule will have much lesser activity. We are just comparing that when you look at the phenyl ring of the phenylpropylamines, it will bind the site D. That's the phenyl ring, just like the the ring A of morphine was binding site D. So that we are only comparing the two. So we are saying, yes, we have opened up the molecule, but we have still retained the phenyl ring, and that phenyl ring is able to bind site D just as the phenyl ring of morphine was able to bind site D. So if you, that's why we are saying, therefore, it's only if we change that structure that will have differences in binding the receptor. They do have very high lipid water partition coefficient and a low fast pass and a low fast pass effect due to they are metabolically stable, and it is not an ester but a ketone, also has a long life. So we are saying, if you look at this, the methadone, you look at methadone, you see it's not an ester. Here it's a ketone. You can see these phenyl rings, very high lipid solubility, very high lipid solubility. Of course, we still have a bit of water solubility. Remember, we always have to have water solubility. The ketone and the nitrogen will allow for protonation, allowing for some water solubility, because the molecule must still go into solution for absorption. But because of that change, whereby we are talking about, it is a ketone, high lipid, it has two phenyl groups. Of course, that is also substituted high lipid water solubility. That it is a ketone, will not undergo fast pass effect, fast pass metabolism, because it's not an ester. Again, it has very high lipid water solubility. It has a long duration of activity, and indeed, it also has good activity. That is a general structure as we had already seen it. That is our general structure, whereby you can see all of them have the phenyl ring, and this other group is the one you are changing. And in most of the compounds, this group is also a phenyl ring, with the exception of propoxyphene, whereby it's a benzyl ring. And of course, these two substituents can change depending on the compound you're talking about. And of course, this here can either be a hydrogen here, this can be a hydrogen, or it can be a methyl group. This also can be a hydrogen or a methyl group, which is giving us either the methadone or the isomethadone, and of course the tertiary amine. So it's the same structure as we had looked at. We are saying the dimethyl amino groups, as we have seen, and most of them, indeed, most of the structures have these dimethyl amino. Of course, there are areas we did see that the terminal nitrogen can be part of a piperidine ring or a cyclic ring with retention of activity. Remember, we did mention earlier when we were looking at other SARs that sometimes when you put the nitrogen as a phenyl ring, as a cyclic ring, the substituents might be larger because the cyclic nature constrains the ring, and therefore you find, although the substituents of the nitrogen are larger, they are constrained, and therefore they are still able to fit the receptor appropriately. So, but we are saying, and most of the optimal group is the dimethyl amino group with maximum for optimum potency. The diethyl amino, where you have an ethyl group and amino group, is less potent. 5 and 6 membered alicyclic basic units have comparable activity to the dimethyl amino group. The 5 to 6 membered alicyclic, 5 to 6 membered alicyclic is where we talked about piperidine ring, we talked about the morpholine ring. So the nitrogen can be part of a 5 to 6 membered alicyclic ring or heterocyclic ring with good activity. So the 5 to 6 membered heterocyclic rings give us good activity similar to the dimethyl amino group. So that's why you find some drugs that do have the heterocyclic 5-membered ring with retention of activity. The 2-carbon chain between the basic nitrogen and the quaternary carbon is the optimal length. Same thing we had mentioned all along, that the quaternary carbon, and even in these ones, I did not want to stress, even these ones, they do have, this is a quaternary carbon, and we are saying we still have, that's a quaternary carbon 1, 2, and that's to draw the structures to see whether they do agree with the morphine rule, and you can still see that's what we are saying, that a quaternary group, an ethyl group or 2 carbon atoms is still what gives you maximum activity. 2 carbon atoms between the quaternary carbon and the nitrogen is responsible for maximum activity. Again, agreeing with all the other compounds that we have looked at. Removal of the 6-alpha methyl. Removal of the 6-alpha methyl, no methadone decreases activity. So again, we are saying if you, for the methadone which has no substitution, again, that reduces activity, and therefore branching. We are saying branching for these compounds is important, and the branching also is depending on the branching we are talking about. So let us look at that again. 6. They counting from 6. Like 1, 2, 3. So it's, if you look at the counting here, it's good to see how why they are calling it the 6. So you look at, they are counting from the ketone. Ketone carries the first priority. So 1, 2, 3, 4, 5, 6. So 6. So that's why we are saying you can have either the methyl substitution alpha, it's an alpha substituent, either at position 6 or at position 5. So that's why we have said removal of the 6-alpha methyl group reduces activity. And of course, we have therefore said that no methadone does not have the 6-alpha, and we have looked at it. Just wanted to qualify why we are calling it 6-alpha, and we have looked at the numbering. We are also saying moving the 6-alpha methyl to position 5 beta gives isomethadone, which has 65% of the potency. So in other words, the 6-alpha, as in methadone, is the one which is responsible for maximum activity. 6-alpha has much higher activity than the 5-beta, where we call it isomethadone. Ketone side chain is important for activity. Removal altering its length abolishes or significantly reduces activity. Again, we had already mentioned this. So this here is our ketone. You lengthen it. So remember, we had talked about this. To the propyl. 1, 2, 3. 1, 2, 3. The propyl group is important. It gives maximum activity, just as in the phenyl piperidines. You abolish it, you change it. That again abolishes or diminishes activity. Again, remember we say the ketone is much better. It's more stable than the ester. So you can see this is the methadone, whereby that has the alpha orientation, giving us, that is the alpha orientation that gives us the levomethadone. And we are saying if we move it to position 5, give it a beta orientation, giving us the isomethadone, that, as we have already mentioned, will give us lesser activity. Mention the ketone, again, important. These groups are important the way they are. It requires to be the proper, to maintain the shape, to maintain the size of this molecule. Because as I said earlier, and I'm repeating again, let us always have it in our minds that the site they are binding is not changing. The site, the receptor, the morphine receptor is standard. It's not changing. It remains the same. So the molecule must maintain the same size as morphine, or the same size as what we call the endogenous opioids, so that it can bind that receptor optimally. So if you put any groups that will change the size of the molecule, change the shape of the molecule, you will interfere with the binding. All the above modification results in changing the distance and orientation of the basic amine and the phenyl group. So once you change, if you do any modification that changes the binding, like the alpha, like we have said, if you put the alpha methyl group at the 5 position, as in isomethadone, you are changing the shape, the size of the molecule. And once you change the size of the molecule, it will not interact with the receptor optimally. When you put a 6-alpha methyl group, as in methadone, you get maximum binding. When you remove totally the methyl group, as in no methadone, again you interfere with the size. you interfere with the size, and the resultant molecule does not appropriately or effectively bind the morphine receptor, and therefore it does not give us the expected activity. Again, also acetylating the alcohol produced more active compounds. You see, we have an alcohol here myself. That is there. This is our acetyl group. What we have done, we have added an ethyl group there. And we had here, this was a ketone. We didn't have that. So this acetylating does not make sense. So let's first leave it there. All we are saying is that if you look at this compound here, it shares the same structure as methadone, shares the same structure there as methadone. The only difference here is that in place of the ketone, it is an ester. It is an ester, and between, of course, there is a branching in the ester. This is an ester in place. Is an ester in place of the ketone, and I think that's where they are saying acetylating, but it is not an alcohol. It is acetylating. We are talk about acetylating. Doesn't make sense anyway. So let's leave the acetylating. Let's say conversion. So we are converting the ketone into an ester with additional ethyl substitution to give us this compound we are calling the levomethadyl. The levomethadyl here is a compound where you look at this was a group that we had. If you look at your methadone again, the methadone here and is CH2, CH3, and a ketone. If you look at the final drug here, there's a change here because it was ketone, sorry, it was C double bond O, CH2, CH3. So this is the acetyl group that we have added. I think that's what they are calling acetylating the alcohol. But if you look at the original, so this is the acetyl group here, what they have brought in, but the original compound was O, or didn't have this O there. It had a C double bond O, CH2, CH3. So once there is that change of a compound, whereby there is, of course, that introduction of that ethyl group, but I'll still check up that structure properly because it's not really adding up. I'll check that structure. I've not checked it up. So allow me to check that and I'll report it next time, because so that we are sure. So we are saying anyway, that structural modification where we have added this ethyl group has given us levomethadyl acetate, which has much higher activity. As I've said, allow me to check that structure. What is most important is the next point, the levorotatory isomer. No, not that one. I want, so that one is still on the same. I want us to look at I want us to leave this first, and we look at the propoxyphene. So the introduction of a benzyl. So this is propoxyphene. This, as I've said, I'll look it up. That is to human. So this, we had mentioned that you have methadone, and in place of one of the benzene ring, you put a phenyl ring, which is a benzyl ring, sorry. So phenyl replaced by a benzyl ring there, and then ketone is replaced by an ester. So you have an ester here, or it's like the reverse ester. It's a reverse ester when compared to meperidine, a reverse ester. Remember, in meperidine, you are starting C double bond O and O. So you have that ester in place of the ketone. So ketone is replaced by an ester, and then methyl has been moved to the B position. So like in isomethadone. So it has been moved to the beta position as in isomethadone. Remember, methadone, methyl group is in that position. So you can see we have done moves that have actually ultimately reduced the activity. The first move is changing the benzene ring into a phenyl ring, reduction in activity, because you will have an influence on the structure. The other thing is that you have changed the stable ketone into a more labile ester. So again, that of course will bring a few problems. And then again, the methadone, which is most active as the 6 alpha, you have changed it in to the 5 beta. So it is the beta. The methyl group is in the beta position, unlike here being in the alpha position. So both of them have the alpha orientation, but it is from the alpha to the beta position. Again, we said change of the alpha methyl group from alpha to nitrogen to beta to nitrogen reduces activity. So you can see the moves that have been done in synthesizing propoxyphene are moves that further reduce the analgesic activity. This is, of course, to try and reduce the abuse potential of that molecule. So the structural modification done on propoxyphene will decrease potency drastically. There will be drastic reduction in activity, and we can be able to explain why one of the phenyl rings changed to a benzyl ring. The ester, the ketone, changed into an ester. The alpha methyl group changed from alpha to beta position of the ethyl. You can call it ethyl diamino, the dimethyl amino ethyl chain. So we can call it 1, 2, 1. So it's 1, 2 carbons here. So the methyl group changed from the alpha position to the beta position of the dimethyl amino ethyl chain. All those, as we have already discussed, will drastically reduce the analgesic activity of propoxyphene, and therefore the introduction of a benzyl creates a second chiral center. Of course, this is a chiral center. This was the first chiral center there by introduction of the methyl group. But the minute you introduce the benzyl group, you introduce a second chiral center that we had already discussed. Introduction creates a second chiral center with 4 possible isomers. The analgesic activity resides primarily in the dextro isomer. So the dextropropoxyphene is the one which will have analgesic activity, and this has the 2s 3r. So look at that is position 1, position 2, position 3, 2s 3r configuration. It is marketed, of course, as the dextro. This is just one of the brands, so we don't need to remember it. Of course, we are saying it will be dextro propoxyphene. It has 1/8 the potency of methadone. Of course, we understand why. We don't need to remember it has 1/8, but we say it will have much reduced activity compared to methadone and even codeine. It has lower addiction liability and toxicity. Lower addiction liabilities. This is because the lower the analgesic activity, the lower the toxicity. The liver isomer, which now will be an enantiomer. Remember, the liver is an enantiomer or a mirror image of the dextrose. So if this was S, it becomes R. If this was R, it becomes S. So the liver isomer with 2R3S configuration was used as an antitussive, which lacks the classic opioid characteristics on a pure, and it's actually just an antitussive. Again, the levopropoxyphene is an antitussive. It has no analgesic activity. The dextropropoxyphene, as we have discussed, it will have analgesic activity, but much lower than either methadone or even codeine because of the structural modification. And then the napsilate salt is used because it is water insoluble and is less likely to be abused through injection. So that is why you can actually use it as a hydrochloride salt or the napsilate salt. And I had already shown you the napsilate salt very low water solubility. You can see that increase in lipid solubility, and therefore you cannot use that drug for abuse. This, I think I will discuss it next time, because I will discuss the miscellaneous, because I will need to mention things like tramadol. I will also discuss this drug as a miscellaneous, the levomethadale and tramadol. So I'll discuss tramadol, levomethadale, and also tapentadol. So tapentadol. Those I'll discuss them under miscellaneous. And I think with that, unless if there are any issues, apart from those three drugs, I'll look at the only drugs I've not mentioned is the miscellaneous, and I want to discuss them. I want to discuss them in their own categories, not mix them up. I'll discuss them in their own categories, and also introduce tramadol, because we have not discussed tramadol, and also tramadol is used for its analgesic activity. We want to look at its structure and see the structural difference. So those three drugs, we'll discuss them under miscellaneous narcotic analgesics. Any question? I think with that, we kind of are almost through. Narcotic within this class, it has very many small drugs, small groups, very many small groups, but the narcotic analgesic one was the biggest. Once we are done with the narcotic analgesic, the other groups, though important, of course, though important, but they are much smaller. The narcotic now for narcotic analgesics, as I've said, we have discussed all the classes. We started with morphine. We looked at the morphine analogs, where we were looking at codeine, codone. Oh, yeah, and then the only one I'll discuss here is the miscellaneous, and then I'll mention something about the antagonists, the naloxone, the naltrexone, and also nalorphine. So I'll mention just something very little about the antagonists, because we have not really discussed them. So we have discussed, as I have said, the morphine itself, and how do you change the substituent within morphine to get the morphine analogs. And at the morphine analogs, we discussed many different analogs, the codones, the hydrocodones, the hydrocodone, the hydromorphones, the morphones, so many of them. And then from there, we went to the morphinates, where we had the levalofans and so on, and the levalofans and so on. And then from there, we went to the benzomorphans, where we had the metazosine, pentazosine, and so on. And then from there, now today we have done the 4-phenyl piperidines, where we have the pyridine as the prototype, the ketobemidone, the bemidones, the prodines, and so on. And then from there now, the last one, which is quite important, the last one, very important, is the propylamines, where we have the methadone. And of course, the methadone is an important drug, mainly used in rehab centers, because it does not precipitate the withdrawal symptoms. When you give it to somebody who has been on morphine, it will have the same effect, but fortunately, it does not precipitate the withdrawal syndrome. And therefore, when you go to, I don't know whether you have gone to Mathare, you will find that in the rehab they use a lot of methadone, because of that very important fact of not precipitating the withdrawal syndrome. Because it is that withdrawal syndrome, when it's precipitated, it is so terrible, it's so serious, that the client or the patient kind of is forced to go back to taking these narcotic analgesics, because they are not able to withstand the withdrawal symptoms, because they are very, very harsh. But methadone has been found not to precipitate those same symptoms, and therefore has been widely used in rehabilitation centers. So that, my dear, so that is the only thing, as I have said, that we have not discussed. The only drugs we have not discussed is the miscellaneous and the narcotic antagonists. And then as I was going back, my granddaughter, as I was going back, I wanted us to appreciate that we have very many. Wow. Don't cry. I wanted us just to appreciate how many other categories of drugs we have, but they are not as broad. They are not as broad as the first. Don't cry. They are not as broad. I was thinking I have the course outline here, but they are not as broad because we are going to look at. We have the general anesthetics. We have the CNS stimulants. Don't cry. We have the CNS stimulants. They have put very many general anesthetic, CNS stimulants, and Parkinsonism drugs, Parkinsonian drugs, and hallucinogens. So we have another 4 categories. So I think next time we should go first. Which one should we go first? I think we can go first the anti-Parkinsonism drugs. So after this, so we'll discuss those 2 categories of drugs and then the anti-Parkinsonism drugs. So kindly classify the anti-Parkinsonian drugs. Classify the anti-Parkinsonian drugs and draw their structures. The anti-Parkinsonian drugs and draw their structures so that now, after I finish, it will take me a very short time to finish the narcotic analgesics. We move on to the anti-Parkinsonian drugs. My little girl is really crying.